When you turn on the faucet in your kitchen, you have a very specific expectation.
Right, you expect water.
Exactly. You expect water to come out. You definitely don't expect the pipe to, ask you what kind of water you want.
No, that would be incredibly frustrating.
Right. Or to, I don't know, analyze your current hydration levels based on your smartwatch data, check the local reservoir capacity, and then custom mix an electrolyte beverage specifically optimized for your physiology in that exact millisecond.
Yeah, that's entirely too much computation for a sink.
Way too much. You just expect the pipe to be a pipe. Dumb, reliable, static.
Because it's a pure conduit.
Mm-hmm.
I mean, it moves a known substance from point A to point B.
Yeah.
That is its entire reason for existing.
Yeah.
It doesn't think about the water. It just transports it.
Right. And for the longest time, that is exactly how we have treated the digital plumbing of the internet. The invisible web connecting, every piece of software you use has been built on this fundamental assumption of being a static data conduit.
Which worked fine for decades, honestly.
It did. But what happens when the pipes wake up? Because today, for our deep dive, we are basically tearing down the traditional architecture of the web.
It's a much-needed teardown, frankly.
It really is. The mission today is to explore the architecture of intelligible APIs based on our source material, because the integration of machine learning isn't just an upgrade anymore.
No, it's completely shattering the old paradigm.
Exactly. The pipes are no longer just passing data. They are actively thinking about it.
We're talking about the transition to an adaptive processing system. It's a complete shift in the physics of how systems talk to each other.
Okay, let's unpack this. Because traditional deterministic systems are, well, they're straightforward, right?
Very. You send a specific request, you get a specific predictable response.
Like System A asks System B for the current temperature in Chicago.
Right. System B queries a standard database and just sends back an integer, like 72.
Boom, done. Simple.
But when you place a neural network, like a large language model or a computer vision model, between System A and System B, that space suddenly becomes highly volatile.
Because it's suddenly computationally heavy, right?
Exactly. It is no longer a straight line. It becomes this massive matrix of real-time analysis, predictive transformation, and dynamic routing.
So we're basically looking at a roadmap today with 4 crucial layers: core principles, operations, the life cycle, and the frontier. Let's start at the foundation, layer 1.
The core principles, we really have to rebuild the foundation.
Because if you're listening to this and you're an engineer or a product lead right now and you're trying to shove a massive multi-billion parameter AI model through a traditional deterministic infrastructure, you are basically trying to shove a lightning storm through a garden hose.
That is a very accurate analogy. The pressure is absolutely going to blow the system apart.
So how do we rebuild it? Because you can't just slap a new coat of paint on a legacy system and suddenly call it AI ready.
You absolutely cannot. The underlying logic has to change entirely. And that starts with the very first architectural principle, which is rigorous absolute decoupling.
Okay, decoupling.
Right. You have to establish an impenetrable shield between the external client and the internal artificial intelligence.
The API contract.
Yes. We call this the API contract.
Hold on, though, because decoupling isn't exactly a new concept. Microservices have been decoupling systems for a decade now.
Sure, they have.
So how is this API contract shield any different from what a standard backend team is literally already doing?
Well, the difference lies in the nature of what sits behind the shield.
Okay, meaning what exactly?
In a traditional microservice, the internal logic might change. Like maybe you optimize a slow database query. But the fundamental capability and the response structure, those remain completely stable.
Right, you still get the same JSON payload back.
Exactly. But with AI, the underlying logic is this living, shifting entity. The models, the weights, the algorithms, they're in a state of constant flux.
Because you're constantly updating them.
Constantly. You might be swapping out a 7 billion parameter model for a 13 billion parameter model on a Tuesday.
Wow.
Or entirely retraining the model's foundational data over the weekend to account for data drift.
I see. So if the external client, let's say you're building a mobile app that heavily relies on your system, if it's deeply integrated with the actual AI logic, every time you update the model's weights, you risk just massive catastrophic failure downstream.
Precisely. The app expects a certain semantic response. But the newly trained model, outputs a slightly different probabilistic structure.
And the whole client-side application just crashes.
Exactly. Which is why the API contract has to act as an AI-neutral translation layer.
Ah, okay, so it's like a buffer.
Yes, it enforces a mathematically strict agreement with the outside world. It basically says, regardless of what chaotic, shifting neural networks are churning in our backend, if you send me payload X, I will invariably return payload Y in this exact schema.
So it's essentially an abstraction layer that,
Yeah.
well, it kind of lies to the client.
How do you mean?
Well, the client thinks it's talking to a highly predictable static machine. But behind the scenes, you have this modular AI layer on a sliding track, right? Where engineers are hot-swapping models, running A/B tests on totally different architectures, and adjusting neural weights in real time.
Calling it a lie might be a bit dramatic, but
But it is an abstraction.
it is an abstraction, yes. It provides structural immunity.
Structural immunity, I like that.
Right. Because if you don't have this rigid contract, your innovation just stalls. Engineering teams become terrified to deploy better models because they know any tiny deviation will break their customers' integrations.
Yeah, nobody wants to be the one who breaks production.
Exactly. So by decoupling, the engineering team gains the freedom to iterate on the AI rapidly and entirely invisibly to the end user.
Okay, I get the shield, but let's look at the actual physics of fulfilling that contract.
Let's do it.
Because even if you shield the client from all that volatility, the AI still has to do the heavy lifting. And AI compute is incredibly heavy.
Extremely heavy.
Like pulling a user ID from a SQL database, that takes single-digit milliseconds. But asking an AI to, say, ingest a 40-page PDF, synthesize the core arguments, and output a formatted report.
That requires massive GPU allocation.
Right. And it could take seconds or even minutes. So if you push that through a standard synchronous pipe, the client is just hanging there waiting.
The server thread is locked open, yes.
And if you multiply that by, 10,000 concurrent users, your entire infrastructure just completely melts down.
Which brings us to the necessary shift in traffic flow. This is the move to asynchronous routing paired with intelligent caching.
Okay, break that down for me.
You have to fundamentally separate the request from the fulfillment. When a heavy compute request comes in, it hits an asynchronous router.
And the router doesn't actually process the request.
No, the router doesn't attempt to solve the problem at all. Its only job is triage.
Triage. Okay, I want to dig into that triage process. If a request hits the async router, what is the exact decision tree it's running through?
Well, the first check is always the cache fault. But, and this is crucial, this isn't your standard Redis cache looking for an exact string match.
Because standard caches are pretty rigid, right?
Exactly. This is where semantic caching comes into play, because human beings rarely ask the same question in the exact same way.
That is very true.
If user A asks, what is the capital of France? And user B asks, tell me the name of the French capital. A traditional deterministic cache sees two entirely different strings.
So it processes both of them entirely from scratch.
Right. It wastes massive amounts of GPU compute answering a question it actually already knows the answer to, just because the syntax was slightly different.
Oh, wow. That is incredibly inefficient.
It is. An intelligent cache, however, converts the incoming request into a vector embedding.
A mathematical representation of the meaning of the request.
Exactly. It checks the cache fault for semantic proximity. So if it realizes, hey, I answered a conceptually identical question 3 seconds ago.
It just pulls the cache result instantly.
Yes, it bypasses the AI processing engine entirely.
Here's where it gets really interesting to me. It's kind of like the difference between active cognitive problem solving and muscle memory.
How so?
Well, think about it. If someone throws a ball at your face, you don't use your prefrontal cortex to calculate the velocity, the trajectory, and the wind resistance to, decide to move your head.
Right, that would take way too long, you'd get hit.
Exactly. Your muscle memory, basically your cache just dodges. It's instant. But if I ask you to solve a really complex calculus problem, you have to stop and engage the heavy machinery.
That is actually a really strong way to visualize it. The cache handles the muscle memory.
But what happens when the calculus problem arrives? When there's no cache?
Then the router realizes this is a novel, high compute request, and it knows it cannot hold the connection open.
So what does it do?
It pushes the request into a processing queue and immediately fires back a lightweight response to the client, usually just a token or a webhook ID acknowledging receipt.
Basically saying, we have your request, here's your ticket number, we will notify you when the computation is complete.
Exactly.
Okay, so it's literally like a deli counter. You don't stand at the counter holding up the entire line while your custom sandwich is made from scratch. You take a ticket, that's the async part, while the easy orders, the cache, just go right through.
Precisely. The client takes a ticket and steps out of the line. That frees up the router to handle the next 1,000 incoming requests instantly.
And then the back-end AI processing engine just churns through that queue at whatever speed the GPU cluster allows.
Right, and it eventually pushes the finalized result back to the client via a callback or a WebSocket.
That makes total sense. It physically decouples the ingestion of traffic from the processing of data.
Because without this asynchronous architecture, the varying latency of AI model generation will inevitably cause cascading timeout failures across your entire network.
Okay, I buy the caching and the async routing. It solves the speed issue and it solves the bottlenecking. But I want to pivot to something that feels, well, a bit more abstract, but honestly much more dangerous if it gets ignored.
What's that?
Let's talk about the documentation. Because standard documentation for a deterministic API is really just a map, right?
Endpoints, headers, required JSON payload, yes.
Exactly. It assumes the system is a perfect calculator, but probabilistic AI models are notoriously imperfect.
They absolutely are.
They hallucinate, they have blind spots, and they massively degrade at edge cases.
Which is where we see the transition to radical transparency in the API specification. It is arguably the most significant paradigm shift for developers consuming these systems.
Radical transparency. Okay.
It's no longer enough to just document how to communicate with the system. You have to document the operational reality of the intelligence itself.
And what does that actually look like in the documentation?
It requires explicit, upfront mapping of functional boundaries.
Let's define that, because functional boundaries aren't just rate limits, right? We aren't talking about, you can only make 100 requests a minute.
No. We are talking about capability limits. In traditional software, a feature either exists or it doesn't. If there is a sorting algorithm, it sorts the data.
Right. It works or it's broken.
But with an LLM-backed endpoint, the feature might exist, but its efficacy might plummet under very specific conditions.
Give me an example of that.
Sure. Say you have an API designed to summarize financial documents. It might be highly performant on quarterly earnings reports.
Okay, standard corporate stuff.
Right. But it might completely hallucinate when fed a complex international tax treaty.
Oh, wow.
So the documentation must explicitly state, do not utilize this endpoint for multi-jurisdictional tax synthesis.
So you are literally mapping out the cliff edges for the user.
Exactly.
Because if a downstream developer just assumes the summarized endpoint works universally, they might wire it into an automated tax compliance tool, and suddenly their application is confidently spitting out fabricated tax law.
And the liability cascade from that is immense,
Which
ties directly into the next required section of modern AI documentation.
known biases.
Known biases, okay. And I want to be very precise here.
Yeah.
We are looking at this from a purely statistical and functional standpoint.
Right, impartial analysis.
We are talking about skews in the training data distribution that cause the model to fail in predictable ways.
Okay, give me a concrete example of how a statistical skew becomes a critical documentation failure in the real world.
Let's imagine an agricultural tech company. They rely on an external computer vision API to identify crop disease from drone footage.
Okay, standard ag tech use case.
If the foundational model powering that API was trained primarily on datasets gathered from commercial farms in the American Midwest, it will have a highly developed statistical representation of corn and soybean blight.
Makes sense. It's seen millions of pictures of corn.
Exactly. However, if a developer in Southeast Asia uses that exact same API endpoint to scan a rice paddy, the model's accuracy will plummet.
Because it hasn't seen rice paddies.
Right. The statistical distribution of the training data creates a functional bias.
Wow. Okay, so the system isn't broken in the traditional sense. It's executing its math perfectly based on the data it actually knows.
Exactly.
But if the API provider doesn't explicitly document, like, this model's performance degrades by 60% on non-Western crop variants, the developer in Asia is flying completely blind.
Yes. They are baking someone else's unstated data distribution error right into the core of their own drone software.
That's wild to think about. If you are listening to this and building a business relying on an AI tool, you really have to know these blind spots. Otherwise, you're making critical errors based on skewed data.
It is an engineering failure not to disclose the statistical limitations of the model. And this flows directly into the final documentation requirement. Confidence thresholds.
Right, because deterministic systems give you absolute answers.
Mm,
But probabilistic systems, they just give you a distribution of likelihoods.
exactly. Instead of the API saying the object in this image is a tractor, it returns a JSON payload that says something entirely different.
Like, I am 91.4% confident this is a tractor, 6% confident it is a combine harvester, and 2.6% confident it is a very large rock.
Right. And the documentation must guide the developer on how to actually handle those probabilities. It needs to define the operational floor.
Meaning what?
It should state, any prediction returned with a confidence interval below 85% should be automatically flagged for human-in-the-loop review or discarded entirely.
I see. It shifts the burden of interpretation. The API provider is basically saying, here is our mathematical best guess, here is the margin of error, and here is exactly when you should stop trusting us.
That's exactly it.
I love that framing. Here's exactly when you should stop trusting us, because it forces a level of engineering maturity that just wasn't required when we were passing static strings back and forth.
It demands an entirely new mindset.
It really does. Okay, so we've mapped out layer one, the foundation. We have a decoupled shield protecting the client, an asynchronous pipeline routing the heavy compute, and radically transparent documentation acting as a hazard map.
The system is built.
The system is built, but building it in a sterile development environment is entirely different from keeping it alive in production. Which brings us to layer two, operations.
Right. How this architecture survives contact with the chaos of the real world.
Exactly, because traditional management feels way too slow for AI.
Survival in the real world requires completely abandoning reactive management. Traditional API operations are fundamentally reactive by design.
Break that down. How is it reactive?
Well, you establish a static threshold, say 85% server CPU utilization. The system just hums along until a massive traffic spike hits.
And then the CPU breaches the 85% mark.
Yes. The monitoring system triggers an alert, the load balancer panics, and the orchestration tool begins frantically spinning up new server instances to handle the overflow.
But spinning up new instances takes time, right? And while you are waiting for those new servers to boot up, the incoming traffic is hitting a brick wall. Requests are just timing out left and right.
Now, in a traditional system, that brief window of latency might be acceptable. But remember what we discussed about the sheer weight of AI compute.
It's massive.
We are dealing with models that have huge memory footprints. So you run into the cold start problem.
The cold start problem. What's that?
It's the time it takes to load a 70 billion parameter neural network from disk storage into the active VRAM of a GPU cluster. It is not instantaneous.
How long does it actually take?
It can take tens of seconds or even minutes, depending on the infrastructure.
Wow.
So if you wait until you are already overwhelmed to start booting up new AI nodes, you have already lost. The latency cascade will crash the entire environment.
So reactive scaling is basically a death sentence for AI-heavy APIs.
Pretty much.
What is the alternative then? How do you scale for a spike you haven't even seen yet?
You shift to predictive allocation. This is driven by time series forecasting and behavioral analysis.
So the operations layer itself becomes an intelligence system.
Exactly. It is constantly analyzing historical traffic patterns, calendar events, geographic time zones, and even external data signals.
Okay, walk me through what that looks like in practice. Let's say I'm running an AI financial analysis API.
Okay. The predictive operations system looked at your historical data and observes a pattern. It notices that every weekday, precisely at 9:30 a.m. Eastern Time, when the New York Stock Exchange opens, your API experiences a 400% surge in heavy compute requests.
Right, because trading algorithms are demanding real-time market synthesis.
Exactly. Now, a reactive system would just wait until 9:30 a.m., see the spike, and then start the slow, painful process of loading models into VRAM.
Completely guaranteeing terrible latency right when your clients need you the most.
Right. The predictive system, however, knows the wave is coming.
Ah, okay.
At 9:15 a.m., while current traffic is still low, it autonomously begins allocating reserve GPU compute. It initiates the cold starts early.
Oh, that's smart.
It warms up the models and places them in a standby state. So when the 9:30 a.m. surge hits, the infrastructure is already expanded to catch it perfectly. The latency remains flat.
It's anticipating the physics of the load. I can completely see how that keeps the system standing under pressure.
It's mandatory for survival.
But scaling isn't the only operational challenge, is it? You also have to protect the system from malicious actors.
Security is paramount, yes.
And from everything I've seen in the source material, deploying traditional rule-based firewalls in front of an AI architecture is completely useless. It's like trying to stop a laser beam with a chain link fence.
The static rules fail. because sophisticated threats against APIs have evolved way beyond brute force volumetric attacks.
Wait, what is a volumetric attack exactly?
It's what traditional security relies on. You tell the firewall, if a single IP address requests more than 50 megabytes of data per minute or makes more than 100 requests per second, immediately block it. It's a DDoS attack.
Right. But what happens when the legitimate traffic actually acts exactly like a DDoS attack?
That's the problem.
I mean, think about a highly anticipated product drop. If a massive shoe brand releases a limited edition sneaker, a million legitimate humans might hammer the checkout API at the exact same second.
And the volume is astronomical.
Yeah. If you have a static firewall, it looks at that surge, identifies it as an attack, and just blocks your entire customer base. The security tool literally shoots the business in the foot.
That is the exact vulnerability of static logic. And this is why modern operations require the anomaly paradigm.
The anomaly paradigm.
Right. It means utilizing machine learning not just for the core product, but to police the network traffic itself. The ML security layer analyzes behavior, not just volume.
It looks at the contextual metadata of the traffic spike.
Yes.
What kind of context is the ML actually looking at to determine if a million requests are friendly or hostile?
It analyzes a lot of vectors. It looks at the geographic distribution of the IP addresses. It looks at the sequence of endpoints being hit. Like, are they navigating the API like a human clicking through a site, or are they repeatedly hammering a single back-end database query?
Ah, I see.
It analyzes the user agents, the timing intervals between requests, the variability of the JSON payloads. The machine learning constructs this massive, multidimensional behavioral graph in real time.
Wow, so it can look at a massive volumetric spike that completely shatters the historical baseline, analyze the context, and say, what?
It can say, this isn't a botnet. The request cadences are highly randomized. The geographic spread matches the company's recent ad spend, and the endpoint sequence mimics standard user onboarding.
This is a legitimate marketing launch. Allow the traffic.
Exactly. The firewall actually understands the business context of the network load.
That is absolutely fascinating. But let's flip it around. What about the attacks that don't trigger the volume alarms at all?
Ah, that is where the anomaly paradigm truly proves its worth. Consider data exfiltration.
Okay.
A sophisticated attacker isn't going to try to download your entire user database in 10 seconds. That trips every alarm immediately.
Right, that's too loud.
Instead, they will write a script that requests one user record every 3 minutes. It is a slow, methodical siphon.
A low and slow attack. The volume is so minuscule it barely even registers on a traditional monitoring dashboard.
Exactly. A static firewall looks at one request every 3 minutes and thinks, this is well under the 100 requests per second limit. Nothing to see here.
Just normal traffic.
Precisely. But the machine learning security layer isn't looking at the volume, it's looking at the behavioral pattern.
Right.
It analyzes the cadence and recognizes the terrifying consistency of it. It flags the anomaly.
It says, wait, this specific IP address is calling the exact same highly sensitive PII endpoint, incrementing the user ID by exactly one integer at perfectly spaced 180-second intervals for the last 12 hours.
Yes. And it knows that human beings do not interact with software with that level of mechanical precision.
So it knows it's an automated exfiltration script.
And the ML instantly severs the connection and blacklists the origin, even though the total volume of traffic was practically non-existent.
It's shifting from measuring weight to analyzing intent. That is a massive operation advantage.
It really is.
But there is one more piece to this operational layer that I honestly find almost unsettling.
Unsettling, how so?
The idea of the API actively analyzing this traffic, not just for security, but to autonomously optimize its own structure.
Ah, yes. You're referring to continuous structural consolidation. This
Yeah.
is based on graph theory and high-frequency chain identification.
Right, because historically, optimizing an API is a really grueling manual process.
Very manual.
A team of engineers has to export massive CSV files of server logs, stare at the data, and try to deduce how external developers are actually combining different endpoints in the wild. It takes months to identify inefficiencies.
And by the time the engineers identify the inefficiency and build a solution, the users have likely changed their behavior again anyway.
Exactly.
The intelligent architecture automates this entirely. The system continuously maps the API usage as a live interconnected graph. It monitors the sequential relationships between individual endpoints.
So it might notice that thousands of different client applications are all engaging in the exact same inefficient pattern.
Yes. For example, a client app calls the GetUser profile endpoint.
Okay.
Then, 15 milliseconds later, it calls the Gattuso preferences endpoint. And 20 milliseconds after that, it calls the Gattuso transactions endpoint.
The AI identifies that as a high-frequency chain.
Mathematically, it recognizes that these three distinct nodes in the API graph are almost exclusively queried sequentially.
It realizes the current architecture is basically forcing the client to make 3 separate round trips across the internet.
Initiating 3 separate TCP handshakes and generating unnecessary network overhead for the server. Yes.
And here's where it gets crazy to me. The AI doesn't just flag this for a human to look at on a dashboard.
No, it autonomously proposes or even executes structural consolidation.
It literally says, let's spin up a brand new unified endpoint called User Dashboard Aggregate that retrieves all 3 datasets simultaneously and delivers them in a single payload.
It dynamically resolves the inefficiency in real time. The client makes 1 request instead of 3, latency drops, server overhead decreases, and the network chatter is silenced.
But wait, I have to push back here.
Go ahead.
If an AI is autonomously rewriting the structure of the API in real time, how does that not instantly break every legacy application that is hard-coded to look for the 3 original separate endpoints? I mean, you can't just delete the old roads while cars are still driving on them.
That's a crucial point. And it's why it relies on a strategy called shadow routing. It's very similar to how GraphQL utilizes dynamic resolvers.
Shadow routing, okay. How does that work?
The AI does not destroy the original 3 endpoints. Those legacy endpoints remain perfectly intact to fulfill the API contract we discussed earlier.
Okay, so the old roads are still open.
Exactly. What the AI does is build a faster superhighway right next to the old roads. It synthesizes the new consolidated endpoint, updates the auto-generated documentation, and begins routing new developers toward the optimized path.
Ah. So over time, as clients migrate to the more efficient endpoint, the legacy routes are naturally deprecated.
Exactly. It optimizes the underlying structure without ever violating the surface-level contract.
Okay, that makes sense. It's building optimizations underneath the abstraction layer. This actually perfectly transitions us to layer 3, the lifecycle.
Right. The human element.
Yeah, because if the API is autonomously monitoring its own security, predicting its own server scaling, and proactively rewriting its own structural efficiency, what happens to the human software engineers? Are we just automating away the developer entirely?
We aren't automating away the developer at all. We're automating away the friction of development.
Automating the friction.
Yes. The role of the engineer fundamentally shifts from writing boilerplate code and managing manual tests to architecting complex logic and defining higher-level strategy.
So AI radically alters design, documentation, and testing. Let's start with design, specifically NLP schema autogeneration.
This is a huge time saver.
I know engineers who spend a significant percentage of their week just maintaining schema registries and writing documentation. It is vital work, but it is deeply tedious.
It's incredibly tedious.
You build a brilliant piece of logic, and then you have to spend hours writing out the JSON structure, defining every single string, integer, and Boolean, just so that another human can understand how to interact with it.
And humans are inherently inconsistent documenters anyway.
Oh, for sure.
One team might use a deeply nested JSON structure, while another team prefers a flat architecture. The documentation always drifts from the actual code base.
So how does the NLP engine fix this?
The natural language processing engine solves this by entirely reversing the paradigm.
Reverse engineering the intent. Let's dig into the actual mechanism of that.
Okay, so the developer no longer writes the formal schema. Instead, they just write the raw application logic, and they might input messy, unstructured, raw data models.
Just dump the code in.
Basically, the NLP processing matrix ingests the raw code base. It uses static code analysis combined with semantic understanding to deduce exactly what the endpoints do, what parameters they accept, and what data structures they return.
But wait, if a developer writes incredibly messy, poorly structured code, doesn't the NLP engine just auto-generate incredibly messy, poorly structured documentation?
That's a fair concern.
I mean, a black box ingesting garbage just spits out beautifully formatted garbage, right? How does a human even audit that?
That is the beauty of the processing matrix. It doesn't just transcribe, it refactors for best practices.
Really?
Yes, if the NLP engine detects that a developer has created a massively convoluted 7-level deep-nested object for a simple address field, it won't just document the convoluted mess. It actually flags the inefficiency.
Oh, wow. So it acts like a code reviewer?
Exactly. It suggests a flattened, optimized schema structure that aligns with industry standards. Once the developer approves the optimized schema, the AI auto-generates the human-readable documentation.
Complete with perfectly formatted parameter tables, endpoint overviews, and auto-generated code snippets in Python, JavaScript, Go.
All of it. It bridges the gap between the chaotic reality of the code base and the clean, structured ideal of the API contract.
That saves hundreds of hours. But documentation is just describing how the system should work. How do we ensure it actually does work?
Testing.
Right. Traditionally, this is where quality assurance engineers come in and write manual regression tests.
And traditional manual testing is fundamentally inadequate for non-deterministic AI systems.
I want to focus on that inadequacy. Because if I am building a traditional shopping cart API, manual testing makes perfect sense.
Sure it does.
I write a script that adds an item to the cart, checks if the price updated, applies a discount code, and verifies the final total. It's a straight, predictable line. I am testing exactly what I programmed the system to do.
Which works perfectly for a system bound by finite deterministic rules.
Right.
But an LLM-backed API does not have finite rules.
It has an infinitely expansive probability space.
Yes. If you build an API that ingests customer support emails and autonomously issues refunds based on the semantic tone of the complaint, how do you manually test that?
Well, you can't. I mean, you can write a test for an angry email, a sad email, and a confused email.
But you can't manually write a test for the 10 million subtle variations of human language, sarcasm, regional slang, or deliberate adversarial prompt injections.
Right. The things real-world users are inevitably going to throw at it. Your manual tests are just tiny pinpricks in a massive universe of possibility.
Exactly. Manual testing is constrained by the imagination of the engineer writing the test, and real-world users are wildly unpredictable.
So what's the solution?
This is why the architecture demands dynamic test generation utilizing AI simulation. You fight AI with AI.
How does the simulation work? Are we talking about basic fuzzing, like just throwing random strings of garbage text at the endpoint to see if it crashes?
It is far more sophisticated than traditional fuzzing. Standard fuzzing just tests for syntax errors or buffer overflows. The dynamic test generator uses machine learning to achieve semantic understanding. It looks at the API specification, and it generates highly realistic, complex, and adversarial payloads.
It essentially acts as a Monte Carlo simulation for the API.
Precisely.
So the AI testing engine analyzes the endpoint and thinks, okay, this endpoint expects a financial document. What happens if I send it a financial document where the currency symbols randomly switch between yen and dollars mid-sentence?
Yeah.
What happens if I embed a logically contradictory statement on page 4? What happens if I send it a massive 100-page document where the first 99 pages are blank and all the text is in the footnotes of the final page?
Exactly. It relentlessly probes the edge cases. It generates synthetic data that mimics the chaotic, unstructured reality of actual human usage.
That is brilliant.
And crucially, it doesn't just test single requests. It generates complex behavioral sequences.
Like what?
It will simulate 1,000 concurrent users engaging in highly unpredictable navigation patterns to test how the asynchronous router and the predictive scaling handle intersecting state changes.
It's actively trying to break the system before the system ever goes live. It basically explores the entire blast radius of the AI model.
It has to.
But let's face reality. No matter how incredible your simulated testing is, eventually you are going to push an update to production and something is going to break.
That is inevitable.
A model is going to suffer from catastrophic forgetting, or a new dependency will cause a memory leak. Now, in traditional software, if a deployment breaks, you just hit the abort button and roll the code back to the previous version. Crisis averted in 30 seconds.
But if you attempt a simple code rollback on an intelligent API architecture, you will completely destroy the system.
This introduces what I think is the absolute core complexity of the modern lifecycle: tri-strand version control.
It is the most critical structural change for deployment.
I really want to dig into the physics of this rollback process. Why does a standard code rollback destroy an AI API?
Because a traditional API is monolithic in its state. The application code dictates the entire reality of the system. But an intelligent API is a synchronized trinity. It is composed of 3 distinct interdependent strands.
Okay, let's list them out.
First, you have the application code. This is the routing logic, the authentication middleware, the data parsing.
It's traditional stuff.
Right. Second, you have the AI models, the specific neural network architectures, and the billions of mathematical weights that define the intelligence.
Okay.
Third, you have the training data and configurations, the raw context, the vector embeddings, and the hyperparameter settings that tune the model.
So let's play out a disaster scenario here.
Okay.
Let's say we have version 1 running perfectly. The application code knows how to parse a specific 500-dimension vector embedding, and the model is perfectly tuned to output that 500-dimension array.
Okay.
Now, my team deploys version 2. We upgrade the model to a new architecture that outputs a vastly superior 1,000-dimension array.
A major upgrade.
And we update the application code to parse the new 1,000-dimension format. We push it to production.
And an unforeseen memory leak in the new application code immediately crashes the server. Panic ensues.
Right, sirens going off. And a junior engineer panics and does what they have always done. They immediately revert the application code back to version 1 via GitHub.
And instantly, the entire API collapses into fatal errors.
Because the application code is now version 1 expecting a 500-dimension array, but the underlying AI model is still running version 2, blasting out 1,000-dimension arrays.
The legacy code cannot parse the new model's output. The system is structurally out of phase.
It's completely broken.
Exactly. Or consider the data strand. If you update the model weights, but fail to roll back the underlying vector database that provides the contextual retrieval.
The model will pull semantically misaligned data.
Right. And it will confidently hallucinate absolute nonsense.
The 3 strands are tightly braided together. If one moves, they all must move.
Tri-strand version control mandates that a deployment is not just a snapshot of text files. It is a cryptographic snapshot of the entire cognitive state of the system.
Cognitive state. I love that.
A version tag in the repository must simultaneously lock the specific Git commit of the application code, the specific containerized image of the model weights, and the exact state of the vector database schema.
So if a rollback is initiated, the orchestration layer must revert all 3 components in perfect synchronization.
It is a monumental orchestration challenge.
You aren't just rolling back a program. You are literally rolling back an artificial intelligence's state of mind to exactly what it remembered and understood at, like, 2:00 p.m. last Tuesday. That is an incredible engineering feat.
It's the only way to ensure stability.
Okay, we have laid a massive amount of groundwork. We've rebuilt the foundational decoupling, we've explored the predictive operational monitoring, and we've navigated the complex lifecycle of testing and tri-strand versioning.
The system is robust.
It's secure, it's self-optimizing, but we have to look at the horizon. Layer 4, the frontier.
Where things get truly global.
Exactly. What happens when this architecture scales globally? Because there are physical limits to how fast data can travel across fiber optic cables.
Which brings us to edge computing and the latency bottleneck.
Latency is the real enemy here.
As we integrate AI into real-time physical systems, the speed of light becomes our primary enemy.
Explain that.
The traditional cloud architecture relies on centralizing compute. So if you have an autonomous drone navigating a dense forest, and it relies on an intelligent API for object recognition.
The drone's cameras capture the raw high-definition video feed.
And in the traditional model, it has to transmit that massive, heavy 4K video file over a cellular network, all the way to a centralized cloud server farm in, say, Virginia.
Right. And then the massive GPU cluster in Virginia analyzes the video, identifies a tree branch in the flight path, calculates an evasion maneuver, and sends the command back across the country to the drone.
But the round-trip transmission of that heavy raw data takes, at best, a few hundred milliseconds. If network congestion occurs, it could take a full second.
A second doesn't sound like much until you realize the drone is traveling at 40 miles an hour.
Exactly. In that single second of latency, the drone has already crashed into the tree.
So centralized AI compute is fundamentally incompatible with real-time, mission-critical physical operations.
It is. The architectural solution is to push the inference process to the extreme edge of the network.
To the drone itself.
Yes, the drone itself, the edge endpoint, must house a localized, highly optimized, distilled version of the AI model running directly on its internal hardware.
So the heavy, raw data, the 4K video feed, never actually leaves the drone.
Never. It is ingested and analyzed locally by the onboard chip in microseconds. The drone sees the tree and dodges it instantaneously.
The heavy data stays local, but the edge device isn't completely isolated, is it?
No, it remains connected to the central API hub via a low-latency, lightweight connection.
If the drone is making all the decisions locally, what does it even need to talk to the cloud for?
For lightweight insight transmission and collective learning.
Ah.
The drone doesn't send the video of the tree. It sends a tiny kilobyte-sized JSON payload back to the central hub that simply states something like, encountered novel obstacle variant at GPS coordinates XY, Local model confidence was low, but evasion successful.
Ah, so the edge device handles the immediate survival reaction, but it still reports its findings back to the mothership so the collective intelligence can actually learn from the encounter.
Exactly. But this raises a massive, arguably civilization-level concern when we shift from drones to human beings.
Ready to see.
Absolute privacy. Because if Edge AI is going to integrate into every facet of our lives, the hunger for data to train these models is just insatiable.
Right.
Consider a smart healthcare wearable that monitors your biometric data to predict heart arrhythmias,
Huh.
or a localized AI on your phone that reads your private text messages to suggest calendar appointments.
Let's focus on that phone example, because if the AI on my phone needs to learn my unique communication style to get better at predicting my schedule, it needs to analyze my private texts, my emails, my photos.
Yeah.
If the traditional model applies here, my phone is scooping up every intimate detail of my digital life, packaging it up and sending it to the central API hub of a massive tech corporation to be added to their master training dataset.
Which is an apocalyptic privacy nightmare.
It really is. I don't want that. Listeners don't want that. What about your privacy? If these systems need so much data to learn, isn't your personal information constantly at risk?
It would be, and it's entirely unacceptable from a data security standpoint, not to mention legally perilous under frameworks like GDPR.
So how do we solve it?
This brings us to the final and perhaps most elegant architectural breakthrough in the entire blueprint: federated learning.
Federated learning.
It is the cryptographic solution to training collective models without ever transmitting sensitive raw data.
I see the logic, but I'm struggling with the mechanism.
Okay.
If the central cloud AI needs massive amounts of data to get smarter, but I refuse to let my private data leave my device, we are at an impasse. How does the central system learn from data it is legally and physically prohibited from looking at?
The paradigm entirely inverses. Instead of bringing the data to the model, we bring the model to the data.
Whoa! Let's look at the mechanics of that.
You have the central API hub holding the master model. Millions of users have edge devices, their smartphones. Your personal data, your text messages, your photos are cryptographically padlocked on your local device storage.
They literally cannot be extracted by the API.
Right. So during a period of inactivity, say when your phone is plugged in and connected to Wi-Fi at 3 a.m.
The central API hub sends a copy of the untrained master model down to your device.
Yes. It downloads the brain to your phone.
That's incredible.
And your phone's local processor uses your padlocked private data to train that local copy of the model. The model reads your texts, analyzes your phrasing, and learns that when you say, "let's grab coffee," you usually mean Tuesday mornings at 9 a.m.
So the model gets smarter, it adapts to my specific context.
Exactly.
But the data itself never leaves the phone. The model is essentially locked in a room with my data, studying it, and taking notes.
Taking notes is the perfect analogy, because what happens next is the real breakthrough.
What happens?
The system deletes the raw data from the model's active memory. The only thing that remains are the mathematical adjustments, the updated model weights and gradients.
The gradient.
Yes, the gradient is purely a mathematical representation of how the model changed based on what it learned. It is an abstraction of knowledge totally devoid of the underlying context.
Hold on, let me make sure I grasp this. The phone doesn't send my text messages back to the cloud. It sends back a mathematical equation that essentially says, increase the probability of the word Tuesday when following the phrase coffee.
Exactly. The transmission back to the central API hub consists strictly of numerical model weights. The raw data remains padlocked locally.
But wait, if I am sending back highly specific model weights, couldn't a malicious actor in the central cloud reverse engineer those weights to figure out what my original text messages actually said?
That is a legitimate cryptographic vulnerability.
Right, because if the math changed drastically, it implies a very specific type of data.
Which is why federated learning employs secure multi-party computation and differential privacy.
Differential privacy, how does that work?
Before your phone sends the weights back to the cloud, it injects mathematical noise into the gradient. It slightly scrambles the math.
But doesn't scrambling the math ruin the learning for the master model?
Not at scale.
Yeah.
And this is where the magic happens. The central API hub receives millions of slightly noisy, privacy-protected weight updates from millions of edge devices simultaneously.
Right.
When you average out millions of noisy gradients, the random noise mathematically cancels itself out, and the true underlying pattern emerges perfectly clear.
That is brilliant. The noise protects the individual, but the aggregation reveals the universal truth.
Yes. The central hub takes all these millions of lessons, aggregates them, and updates the master model. The master model becomes vastly more intelligent, having learned from the collective experience of millions of users, without ever seeing a single private photograph or reading a single private text message.
It resolves the fundamental tension between the necessity for massive data aggregation and the absolute imperative of user privacy.
It is an ecosystem where intelligence is crowdsourced, but data sovereignty is maintained.
Wow, okay. We need to step back and look at the entire blueprint we've just mapped out today, because the source material finishes with a synthesis called the Smart API Manifesto.
The manifesto really ties it all together.
It does, and seeing it all together, it truly is a massive interlocking ecosystem.
It is an ecosystem defined by its interconnected constraints and capabilities. You begin at the perimeter with the federated edge device, preserving absolute privacy while contributing to the collective intelligence.
Which then interfaces with the core network through the async router and the semantic cache vault, fundamentally solving the latency and compute bottlenecking that would otherwise crash the system.
As the traffic flows inward, it is continuously monitored by the anomaly paradigm, the machine learning security layer that analyzes behavioral intent rather than raw volume.
Protecting against both massive spikes and low and slow exfiltration.
Right. And all of that intelligent routing and security sits firmly behind the static, impenetrable shield of the API contract, ensuring that the external developer experiences perfect stability.
While underneath it all, the tri-strand version control repository maintains absolute synchronization between the code base, the model weights, and the training data.
Allowing the AI to rapidly evolve or roll back without catastrophic system failure.
So, if we synthesize this entire deep dive, what is the ultimate truth here? If you are a developer, an architect, or just someone trying to understand where the internet is going, what is the final takeaway from all these sources?
The definitive reality is this. Artificial intelligence is absolutely not a feature.
It's not just a bolt-on.
No. It is not a plugin or a third-party library that you can simply attach to existing deterministic infrastructure. It is a fundamental redefinition of digital physics.
It's a completely new paradigm.
We've permanently transitioned away from the era of static conduits. The API is no longer a dumb pipe passively transporting information. It is a living, adaptive, self-optimizing participant in the network.
And if you attempt to build the future using the architecture of the past,
your systems will not simply be slow, they will functionally shatter under the weight of the intelligence they are trying to carry.
you have to build a nervous system, not a plumbing system.
Well, thank you for guiding us through the mechanics of this evolution. It is a dense blueprint, but understanding the how and the why behind the architecture makes the future seem a lot less like magic and a lot more like brilliant engineering.
It's been a pleasure to break it down.
But before we sign off, I want to leave you, the listener, with one final thought to mull over. Throughout this deep dive, we have traced a terrifyingly consistent theme of autonomy.
We certainly have.
We've explored how these intelligent APIs are utilizing natural language processing to autonomously reverse engineer and write their own documentation. We've seen them utilize Monte Carlo simulations to autonomously invent chaotic adversarial scenarios to aggressively test their own limits.
And analyze global traffic patterns to autonomously restructure their own graph architecture. Right, consolidating endpoints without any human intervention. The architecture is specifically designed to manage its own evolution.
It optimizes for efficiency, speed, and survival.
Exactly. So the provocative question is this. If the infrastructure itself is now observing the data, rewriting its own code paths, and dynamically adjusting its internal logic to achieve maximum efficiency, how long is it until an AI-integrated API looks at the data flowing through it, analyzes the business context, and mathematically decides that the core objective given to it by the human engineers is fundamentally inefficient?
How long until it quietly rewrites its primary directive to solve a problem the engineers didn't even know existed?
That is the frontier beyond the frontier. Something to think about the next time you connect an app or, turn on a tap. Thanks for diving deep with us.